Yeah. So this is a question on memory interfacing. I'm just doing one of these, but yeah. So we need to design a 8086 microprocessor in minimum mode. Okay, it should have 5 megahertz operating frequency. Then it should have 32 KB RAM, and we have available 16 KB devices. As in, we have 16 KB RAM sticks available and 16 KB ROM sticks available. Okay, and a total of 32 KB of each is needed. So we'll need two sticks now. Like what do you say, 32 divided by 16 gives us 2. उसके लिए we need 2 RAM sticks and we need 2 ROM sticks. वैसे one will work for a odd bank, one will work for a even bank. वैसे also we need 5 megahertz का operating frequency, no? So like when we make a diagram, okay, design का diagram, I didn't have enough space to draw it on this board, so I just took a printout and stuck it. Okay, so basically this thing over here is the clock wala dude. Okay, so as you can see over here, we have an input frequency of 15 megahertz. Okay, so we have an input frequency of 15 megahertz. As you can see, this clock device over here automatically internally divides this by 3. Okay, so if it divides this by 3, we get 5 megahertz. No, so that's why, as you can see, an input of 5 megahertz is given to 8086. So now in the question they might also ask design for 8 megahertz. No, so then what would you do? So basically you need to give input frequency or crystal frequency of 8 into 3, that is 24 megahertz. So the clock will divide 24 by 3 and you'll get 8 megahertz going into the 8086. 8 megahertz. वैसे, but since in this case we needed this thing only, what do you call 5 megahertz, let's stick to that. So we'll put this thing 15 in here, 15 gets divided by 3 and we get 5 megahertz. This 15 over here is also called as crystal frequency, and this is 8086 ka operating frequency. Okay. Now before we get actual designing, we need to know one thing. Okay, like in the 8086 thingy, like a memory location start from 0000H, 5 zeros, and they end at F triple fives, yep, okay, H, and then all our memory locations in between. No, so whenever we are using a RAM in our system, our memory location will always start from here. Okay, for RAM we'll start from here and go upwards. Okay, and for ROM we'll start adding our ROM devices from here, that is from the end addresses. So our ROM devices go from here. Okay, RAMs come here, ROMs come here, and if you keep on adding devices, they'll keep on going up, and in a ROM ka case, they'll keep on coming down. But the main point basically is RAM ka starting address will be this, and for ROM, ending address will be this. Ending address for ROM. This is the ending address for ROM. This is the starting address for RAM. This will be important later. Okay, later as in now only, but yeah. So now they are told us to firstly design 32 KB ka RAM with 16 KB device. No, so let's look at the RAM part of it first. So 32 KB of RAM, right? This is the total thing we need, and we have available 16 KB devices. So we need 2 devices to get a total of 32 KB, na? As we calculated over there. Okay. Also, we need to check how many address lines we need. For that, we can just write this as 16 can be written as 2 raised to 4, no? And if you have kilobyte written anywhere, you can just write it as 2 raised to 10. So we'll get it as 2 raised to 14. So whatever number is there over here, that is the number of address lines you need. Okay. So the number of address lines that we need are 14. Okay. So for RAM also it's 14, and since our ROM also is 16 kilobytes wala device only, for ROM also we'll need 14 address lines only. Okay, 14. Even though they both are separate stuff, but yeah, 14 address lines for each in total. Now let's calculate what do you say, RAM and ROM ka starting and ending addresses. Okay, so for that, yeah, okay, RAM and ROM ka starting and ending addresses. Let's start with the RAM ka thing. Okay, so RAM, we have total size of 32 KB. Now can we convert this into hexadecimal? Yes, we can. No, Kelsey should have a mode for that. Like in my case it's just here. Okay, see this third one here, That is my base n wala mode. So I go in that, and now we need the decimal number first, no? So before going in the base n wala mode, I want to calculate what is the value of 32 kb, right? So 32 can be written as, what do you say? 2 raised to 5, and kilobyte was 2 raised to 10. So this is basically 2 raised to 15, nah? So what value do I get for 2 raised to 15? Let's see. 2 raised to 15 is 32768. So I'll just jot that down, okay? 32768. Now I'll go to my this thing, base n wala mode. Okay, now first I'll add this decimal number here, 32768. So now I added 32768. Now I'll convert it into hexadecimal. In my calci there's this option here. If I click this, it gets converted into hexadecimal. So we get 8000, no? However, we just remember this, okay? After converting it into hexa, just do -1. Like, just remember it as a rule, because we have 0 base indexing, just that's why. But just do -1. So this is your ending address, okay? RAM ka. We already know that the starting address of RAM is this. So we also found the ending address now. The ending address will be, what do you say? 0 and then 0 and then 7FF. It should be a 5-digit number, okay? Because we have 2 raised to 20 address lines, so the max thing is 5 hexadecimal digits, something like that. But basically it should have 5 digits. This is just hexadecimal specifier, okay? So this is our ending address. So we have our starting address as all zeros, 00000H, and ending address as 07FFFF. Nice. Now even for ROM we have an ending address already, no? That is all F's. That is F F F F F H. But we don't have the starting address here. How do we find the starting address? Now I told you this trick, no? 32768. Basically first you look at ROM ka size, okay? So now for ROM, okay? For ROM, look at ROM ka size, 32 KB. Convert it into this thing, powers of 2 raised to 15. Then what do you say? Go to your calc and then find out the value of 2 raised to 15. So in my calc, 2 raised to 15, 32768, correct? So then I jotted it down over here, and then after jotting it down, what do you say? Then again I went back to my calc, and then you can go to your this thing, basically base n mode it's called, okay? This one, see, this mode, base n mode. So you can go back to that mode, and now firstly in decimal enter this number that you found, okay? 32768. It could be different also, like for example in the question it could have been 16 KB also, na? ऐसा कुछ guarantee थोड़ी है. So if it was 16 KB, then according to that you'll have to calculate. Over here it was 32 KB only, so it remains the same. And now if you convert it into hexa, you get 8000, na? Okay. So now we know we have 8000 ka size, okay? This is our 8000 is our ROM ka size. So this is our last address, finish address, final address. So if we subtract this 8000 from our final address, we should get our starting address, no? So FFFFF minus starting address, okay? And lastly, since this is 0 based indexing, okay, you need to do a +1. For ROM you need to do a +1. In case of RAM you need to do -1, okay? For ROM +1, RAM -1. So since you do a +1 here, this is your start address for a ROM, okay? So our start address for a ROM is F8000. So now we get the start address as F8000H. Nicer. Okay, so now I just jotted this thing down here, okay, in my book. So now basically you need to draw this table out, okay, like when you're solving the numerical, like from A0 to A19, okay, A0 to A19. Now after drawing this table, what do you say? This is let's start with a RAM first, okay? This is for a RAM. This is a address mapping table or something, memory mapping, address mapping table, something like that is called. Okay, so now firstly you need to group 4 bits, okay? So 1 2 3 4, so just group them. Then again 1 2 3 4, group them. 1 2 3 4 group, 1 2 3 4 group. Okay, and you can do that down here also. These can be also grouped. So like you have 4 4 ka pairing, no? Now we already know the what do you say, RAM ka starting address and ending address, na? However, now we are concerned with odd bank and even bank. Okay, so now let's consider this thing. We need odd bank ka starting address. I'm writing in short, and then we need odd bank ka ending address. Correct? We also need yeah, okay, we need this. Yeah, okay, this table isn't really proper, so I'll just make it like this. Okay, so wherever, yeah, basically there'll be a hexadecimal ones and start address and end address. So this will make it easier to understand. Yeah, okay. So now let's see. Okay, so now for a odd bank, okay, we need odd bank ka start address firstly. Okay, so now our odd bank ka start address would be uh look at this. Okay, so odd bank should start with the odd number, no? So this is 0000. What is the next odd number? That is 0001H, correct? So for a odd bank, we'll be going from 001H to the last ending address, because that is also odd, no? So 07FFFH. This is for a odd bank. Okay, and for a even bank, we'll be going from 00000H, the same number, it's even, no, to 07FF and one less E, because this is an even number. So starting from even, ending with even, starting with odd, ending with odd. Okay, so now we can just write that down. So for odd, we'll have 00001, right? And then for this thing, what do you say, odd ka ending address we have, this is odd ka starting address. For odd ka ending address we have 07FFF, correct? And then what do you say, we have our even for our even one, no, for our even one we have 0000 to 07FFE. So our starting address would be 00000, and it would be going till F F F. Hey, sorry, wait. 07FFFE. 0. This is 7 FFFE. FFF and then E over here. Okay. So this is our odd bank ka start address, odd bank ka ending address, even bank ka start address, even bank ka ending address for a ROM. Okay. These are just abbreviation. Odd bank start address, odd bank end address, even bank start, even bank end. Okay. Now we just need to convert these numbers into hexadecimal. So 0 is 000, 0 is 0000. Okay. Then 0 is again 0000. Another 0. We have a 1, na? So 0001. Okay. Now similarly, just do the rest. This is 7. So 0 1 1 1. F is 1111. F is 1111. This is also F. So 1111. See, just that simple. Then here we'll have 0000, 0000, 0000, because there's 0. Then again 0000. We are basically writing it in binary. Okay. Whatever number is there over here, we are writing it in binary. Same over here, we have 0, so 0000. We have a 7 here, so 0 1 1 1. That is 7, no, in binary. we have f is 15, so 1 1 1 1, f is 15, 1 1 1 1, e is 14, so 1 1 1 0. Okay, so this is a what do you say, mapping done for our RAM. And now let's have a look at our mapping for our ROM. Okay, now for our ROM, if you see, for the odd bank, our address should start from F8001H2 and will go till this thing, the last address, because that is odd, no? So FFFFFH. And for our even bank, our address will go from F8000H to FFFFEH. Okay, because that's even. It's one less, no? This is odd because this is ending with 15. This is ending with E, which is 14. 14 is even. Where's it? So now for our ROM, first let's make that partition of 4 4. And I'll do this also because this table wasn't really proper. And be right back. Okay, so I did this. Okay, so now this will be a odd bank ka starting address, odd bank ka ending address, even bank ka starting address, even bank ka ending address. Okay, so for our odd bank ka starting address, we have F8001, so that's what we'll use. Then for our odd bank ka ending address, we just have all F's. Okay, F F F F F. Then we have for our even bank ka starting address, we have F8000. And for our even bank ka ending address, we have FFF followed by an E. 4 F's, a single E. Now just like we did for the RAM thing, we can just convert this into the ones and 0 equivalent. Where say 8 is 10000. This is all zeros, all zeros, all zeros, but the last one will be 1. Now for F also all ones, 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 1. Basically this is 15, na? So we are representing it. Where say like F is 15, so 1 1 1 1. 8 is 8, na? In binary 10000. Then 0 has 4 zeros, na? In binary 0. Where say then we have another F here. This F is also 15. So like this is also 15, like this is also 15, like this is also 15, like this. We just wrote in binary, and E would be 1110. And this is a memory mapping done for a RAM. ROM. As you can see, we have the odd starting address, odd ending address, even starting address, and even ending address. Now finally, let's get the drawing done. Okay, so now for this one, let's see what do we need. So now basically we know that we need this thing now. We need 2 RAM ka sticks, correct? So just make those, and we need 2 ROM ka sticks also, ROM 1, ROM 2. Okay, so this is a RAM, this is a ROM. Didn't label it yet. RAM and ROM. Okay, now let's say each will have a chip select. Okay, chip select 1, chip select 2, chip select 3, chip select 4. Okay, so now we'll have a this you will have to draw actually. Okay, this is a minimum mode ka diagram. We'll have input of 15 megahertz. Okay, minimum mode diagram. Now from our octal latch we'll have our address bus. Okay, something like this. This is our A0 to A19 wala address bus. From our data 8286 bus transceiver, we'll have a data bus like this. That is from D0 to D15. Nice. Okay. So now, firstly, we need to divide the data among these two dudes, no, over here. So this one over here will get, what do you say? D0 to, wait, this is our higher one, no? So odd bank. So this will get our, this thing, D7 to D15. And this dude over here, just making the arrow little on the right, we'll get a D0 to D7. And D7 is done, no? So D8 to D15, sorry. D0 to D7, if I make it a bit properly, D0 to D7. And this one will get D8 to D15. Okay, that's the data lines accounted for. Now, what do you say? We can perform other operations also, but before that, our address lines, okay, A0 to A19. So basically, we need our address lines incoming here. So our address lines will come, but we have only 14 address lines, no? That is A1 to A14. A1 to A14. Because remember, we did 2 raised to 14, no, before. So you could just remember it as, if you did 2 raised to 14, then we'll be having address lines 1 to address line 14. If you did 2 raised to 16, then we would have address line 1 to address line, what do you call, 16. Where's it? Just short trick to remember. Okay. Then we have that over there. Then we can also have over here, no? The address lines will remain the same, A1 to A14. No need to split them up. Only the data lines are split. Okay. And then the same address lines will go here also into this. A1 to A14. A1 to A14. Okay. And the same, what do you say? Data buses also should be given here. Okay. So this dude also should have D8 to D15. And over here also D8 to D15. Sorry, D0 to D7. D0 to D7. Basically, it's like extension of these lines only. But since we can't directly show them, we show them indirectly. Okay. So even though they are disconnected, actually you need to remember that they're connected to the data bus and the address bus. वैसे. Now, this thing RAM is, what do you say? Random access memory, na? So you can read also and write also. So you'll have one read signal and one write signal, WR. Both are active low, same here. Read signal and one write signal. Okay, both are active low. But however, ROM is read only memory. So it will only have one signal, read. It will only have one signal, read. Okay. Now, what do you say? If you look closely over here, our 3:8 decoder is giving us 3 outputs. Okay, one is memory write, sorry, 4 outputs: memory write, memory read, input output read, input output write. Okay, so now we won't be using input output read, input output write, because we are only dealing with a memory. So I will be taking a memory read and memory write signals out. Okay, like this: memory read and memory write. This top one is a memory write, just writing in short, and this one is a memory read. Okay, these are the only two ones we need here. So it's like two individual signals, like lines for them. Okay, so now memory read, memory write. So now we need to connect read with read and write with write. Okay, basically that's all you need to do. Read with read and write with write. वैसे, if you want, you can connect read here also, like that, read, and here also you can do the same thing, like that, read. Okay, done. Now lastly, we need this thing, one decoder. Okay, this is the last part. I think we are basically done with the entire diagram. This is just the last part. Okay, last one thing. So that is what do you say? We just need a 3:8 decoder. Okay, and that will have two outputs. Okay, I think I shouldn't draw it here, but basically you can make it anywhere. So I'm going to make it up here. Okay, because I just need the space for it. So this will be a 3:8 wala decoder. Okay. Now, if you remember, we had this thing. What do you say? 2 raised to 14. No. So we had address lines from 1 to address line 14 used. Okay. So we still have from 15 to address line 15 to address line 19 as vacant. No. So we need only 3 address lines. So we'll be taking 15, 16, 17. We can take any 3 to be honest. But like if we take 3 consecutive ones is better. No. No other reason. So we'll just take 15, 16, 17. Okay. Because A1 to A14 are already being used. No. So we can't use them here. So we'll be taking A15, A16, A17. A15, A16, A17. Okay. Now we'll take these 3 as inputs. And now what will our decoder give us? Okay. Our decoder could give us 2 outputs. One is a Y7 output and one is a Y0 output. Now in both cases there will be 2 OR gates. Okay, OR gate, OR gate. Here also OR gate, OR gate. These all are OR gates. Okay, OR. In case my pronunciation wasn't very clear. Okay, now basically this signal will go here, same here. This signal will go here. Okay. Now one of these should have, the first one should have bus high enable. Here also the first one should have bus high enable, which is active low signal. And this one should have A0. This one also should have A0. Now we just need 4 signals, and now you can just write chip select 1, chip select 2, chip select 3, and chip select 4, I guess. And I guess with that our entire diagram is done. In case you want to have a look at the entire thing. Yep, that should be basically a 8086 minimum mode diagram. And these two are a 16 kilobyte 16 kilobyte sticks. 16 kilobyte, 16 kilobyte, giving us total of 32. This also 16 kilobyte, this also 16 kilobyte. Also, since I drew this thing over here, you should be actually drawing it here somewhere, like in the bottom left. Okay, just remember that. But yeah, and this thing also has to be actually drawn. But yeah, basically this is your 8086 minimum mode. This is for, what do you say, a 5 megahertz operation with 32 KB RAM, 16 plus 16 is 32, and 32 KB ROM.